Okay, so we're going to continue on with 8.3 and we'll do part 2 here. Part 2 here we're going to call, and in part 2 we are going to actually use what is called the washer method. Okay, so when we went ahead and spinned like the cones and the cylinders, and example number 2, we did this. We had solid discs. There was solid discs, right? In other words, when we twirled it around, we ended up with things that looked like this. Okay, that would what would have looked like. Okay. So in example number 3, we want to find the region in the first quadrant enclosed by the y-axis and the graphs of cosine x and sine x, and revolved around the x-axis. So we're going to go ahead. This is example number 3. Example number 3, we are going to, so cosine x is going to look like that. Sine x is going to look like that, and it meets here where when pi is equal to, when x is equal to pi over 4, right? Where cosine, so sine, in other words, sine pi over 4 is equal to cosine pi over 4. They are all the same value, okay? So we are spinning around this guy here. This area here is what we're spinning around, okay? So we're going to spin this around like this. In other words, our segments are going to look like this, right? And we're going to spin this around the x-axis. So what are we going to have? We're going to actually have a shape of a washer. We're going to look, it's going to, when we spin this around, it's going to look like what? We're going to go from here, right? But we're going to have an inside part here, right? That is missing because this part here has been taken out. There's nothing here, right? We're taking this guy, this strip, and we're rotating it around, right? If you go to page 408 on figure 8.23, it shows you there on that pink little looking thing there, and it looks like a washer. Okay, so how do we find the area of this, or the volume of this washer? Each volume of this washer is what? I'm going to take, if this here is the outer radius, we'll call this the outer radius, and from here to here is the inner radius, is what? So the actual, what am I having? I have pi, the outer radius, minus, I'm going to take away the inner radius, right? I'm taking the inner, what's over there, the inner radius, right? Which is basically what? Pi r(O) squared minus pi inner squared, right? Right? You see that? Okay. So let's look at over here. What do we have here? The top, or the outer radius is what? This is y is equal to cosine x, right? Y is equal to cosine x. So I'm going to get pi cosine squared x, right? Because that is the outer radius, right? Then I'm going to subtract from that the inner one, which is this guy, right? And I'm going to take this from 0 to pi over 4 and multiply it by the thickness, which is dx, right? Okay? So this is what we're trying to do. So I'm going to pull the pi out first. I'm going to get pi 0 to pi over 4 cosine squared x minus sine squared x dx. And if you remember here, the trig identity is this guy. Oh, this is sine squared x, right? Sine squared x. Okay, so this guy gets replaced by cosine 2x dx. So you get pi, what is the, so I'm going to get what? Sine 2x divided by 2, right? I have to divide it by 2 because of the chain rule, so that 2 little 2 there, right? So that's what I would get, and I'm going to evaluate this from 0 to pi over 4. Okay, so what do I get here? If I put x pi over 4, I get sine pi over 2, which is 1. So it's going to be pi over, well, yeah, so I'm going to get what? Pi, so that would be 1, right? So it would be 1 over 2, 0, pi over 2. So pi over, not 4, pi over 2. Is that the answer? Pi over 2, yeah. Okay? So that's how that works. Okay? Key trick being here is this guy. All right? Okay, now let's go ahead and do example number 4. Example number 4 is going to give us another new prospect or new dimension here. In example number 4, all of our revolving volumes or revolutions have been across the x-axis. But just as you can do it over the x-axis, you can actually revolve things around the y-axis, or a vertical axis versus a horizontal axis, okay? So example number 4, the region bounded by the graph of y is equal to 3 times the root of x over 4, the x-axis, and the line x equals 4, okay, is revolved about the axis line that to generate a solid. So let's go ahead and draw this out. We have something that looks like this, and this is y is equal to, what was it? 3 root x over 4. And then I'm going to have x equals 4. Okay, so I don't need this part anymore. And I'm rotating this guy around this axis, right? I'm going this around this axis. So I'm going to slice it this way, right? I'm going to slice each one will be this way. So in other words, I'm going to end up with a, what? What is my height of the disc that I get when I rotate this around? It's going to be a dy. Uh-oh. So we got a dy here, okay? Versus the dx's that we've been dealing with before here, right? So I have to find the radius of this. What is the radius of this? So since this here is x, right? The radius here is what? Is 4 minus x, right? So the radius is 4 minus x, right? So I'm going to go around here, and I'm going to get what? 4 minus x squared pi dy, right? And y goes from where to where? Y goes from 0 to 4, right? 0 to 4, okay? Well, the only problem is here I have an x here, so I have to realign this to have something with an x, right? So I have to solve this for x instead of y. So I'm going to get y over 3 squared is that. So x is going to be equal to 9 over 4y squared. So what do I get here? I'm going to get, pull the pi out, 0 to 4, 4 minus 4, 9y squared. And I'm squaring this dy, right? Okay. So I'm going to pull the 4 out here, but I have to square it so it becomes 16. So it's going to be 16 pi 0 to 4, 1 minus 1 over 9y squared, 2, goes like that. Rather than leaving the 9 in here, I'm going to pull the 9 out also. But I have to square it, so it's going to be that. And this will be 9y squared dy. Okay. So what do I have here? I'm going to end up with 1681 pi's on the top. 81 minus 18y squared plus y to the 4th, 0 to 4, 16 pi, 81, 81y minus y cubed, 0 to 4. And if we do that, we get 128 pi over 5. Okay? So a couple of hard things here. A couple of things that were kind of hard, not only hard, but kind of new, all right, is that when you rotate around a vertical axis, okay, you're going to get dy's. Just as when we were rotating around the x-axis, we had dx's. When we rotate around here, we're going to have dy's. Okay, when we do the wash or slash disk method. Okay, all right. So this is what it's going to look like. All right. So that was kind of a tricky thing. Doing this was a little tricky, I think. And then we have to go ahead and solve this back into here. Once you get here, it's just kind of mechanical stuff over here, so it's no big deal. But setting this up is the hard part. Okay? So since you guys are going to kind of struggle a little bit on the homework on this section, I'm going to do a couple of the homework questions with you for a bonus on you guys. So let's go to, see if we can go to the homework section, and we will do, let's do number 9 together. So we're going to do number 9 together. In number 9, it says, find the volume of the solid generated by revolving the shaded region about the given axis. Okay, so in number 9, it says, we are going to have, what are we doing here? We are, x is equal to 10, x is equal to 10, what? Pi over 4y. Okay, and the region is from here to here, from 0 to 1. 0 to 1, and I am rotating this about the y-axis. So I'm rotating about the y-axis, right? So I'm rotating about the y-axis, which means that I'm going to have slices that look like this. Okay, so obviously we're dealing with a dy situation here, right? Okay, so what is the radius? So what the radius here is going to be, this is x, right? The radius is going to be, so for the radius of each of the disks that I'm going to get is going to be x squared, right? So I'm going to get dx, but I'm going to go from, not dx, dy, right? Times dy, and I'm going to go from 0 to 1, 0 to 1, right? 0 to 1, okay, because y is going from 0 to 1. But now I have to go ahead and put this guy in here, right? So I'm going to get what? Take the pi out, 0 to 1, 10 squared pi over 4y dy. Okay? Well, what am I going to do with this here? Okay, so how am I going to solve this? So what do I have here? I have cosine squared x plus sine squared x is equal to 1. I have tan squared here, so in order to achieve a tan squared, I'm going to have to divide everything by cosine squared. So 1 over cosine squared is going to be secant squared x, right? So tan squared x is, if I move the 1 over, tan squared x is secant squared x minus 1. So this is the same as 0 to 1 secant squared pi over 4y minus 1 dy. Well, what do we achieve here? We have this. We know this, right? This, because the antiderivative of secant squared is what? Tan, right? So we're good with that. So this is what we accomplished here. So this is going to be equal to pi 0 to 1 tan. We're taking the antiderivative here. So you get tan pi over 4y. But from the chain rule, I need this guy, right? You need that guy, right? Then you have minus 1, so this is going to be minus not x but y. Since we're evaluating y, 0 to 1, pi, so if I put pi over 4, when tan is equal, when y is equal to 1, I get tan pi over 4, which is actually 1 times 1 minus 1. When I put 0 in here, I get 0 here, I get 0 here. So what do I get? Pi's cancel out, I get 4 minus pi. 4 minus pi. So my answer is 4 minus pi there, okay? So that was number 9, and let's do number 18. I'll do number 18 with you. So this was number 9, okay? So we're going to do, now we're going to do number 18. All right, let's do number 18. 18. And number 18, it says, find the volume of the solid generated by revolving the region by the lines and curves about the x-axis. So we're rotating about the x-axis. 18, we have y is equal to 4 minus x squared, and y is equal to 2 minus x. So y is equal to 4 minus x squared. It'll look like that, right? 4, 2, negative 2, y is equal to 4 minus x squared. And then we have y is equal to what? 2 minus x? 2 minus x. 2 minus x, so this is 2, 45 degrees. Actually, wait a minute. Where am I at? Okay, so actually this goes down to here, right? Right answer, just not drawn to scale here, right? So we have 2, right? So this is y is equal to 2 minus x. So we're going to take this region here, and we're going to rotate it around like this, okay? So each of my strips are going to look like what? My strips are going to look like this. Okay, so we're going to have a dx here, right? Dx. Where the outer radius is the top, the inner radius is the bottom. So we're going to go pi, outer radius is this guy up here. So it can be 4 minus x squared squared, right? And the inner radius is going to be this guy here, right? So it's going to be minus 2 minus x squared dx. Okay, and we're going from where to where? We have to find that out. So we know here, this is 2, so we know that. This is 2. We need to find out where these two meet right here, right? So we'd have to be able to solve, put these equal to each other and solve it. So we're going to have what? 4 minus x squared, 2 minus x. So I move the x squared over here minus x. Move that over here, minus 2 is equal to 0. X minus 2, x plus 1 is equal to 0. So obviously this guy here is going to be negative 1 right here, right? The other one is over here, right? We already found that. We already knew that. Okay, so we have negative 1. So this is going to be from negative 1 to 2. Okay? So the rest is just mechanics, so let's see if we can do it. We have, I'm going to pull the pi out. Negative 1, 2. Square that. 16 minus 8x squared plus x to the 4th. Minus 4. I had minus 4x. The minus, I'm going to get plus 4x. And then I had x squared. Now it's going to be minus x squared dx. Right? So we're going to get pi 1, 2. I get 12. And then I get minus 9x squared, right? Plus 4x plus x to the 4th dx. Pi, take the antiderivatives here, I get 12x minus 3x to the 3rd plus 2x squared plus 1/5 x to the 5th. I'm going from negative 1 to 2, right? And we're not going to do the whole thing. If you do that, you're supposed to get 108 over 5. 108 over 5 pi. Okay? And we'll stop here today.